third or fourth student for this afternoon is Chantang. He will tell us about homotopy theory and fundamental group. Please, you can start.
Okay, good afternoon, Dr. Monir and Dr. Dulik. Okay, my presentation title is Homotopy Theory and Fundamental Group. Okay. Okay, today I will talk about the homotopy theory. First, I will give some properties about the homotopy. Then I will define the fundamental group of a space. Then we'll see the fundamental group of the circle. Then we will talk a bit about Van Kempen theorem. If we have time, we can talk more about this. Okay, now we talk about the homotopy theory. Okay, the homotopy means we want to focus on the deformation of a function. Okay, we can consider f is a f map, a continuous map. Fg is a continuous map. So there's a two path there. So we consider as the how can we process the f go to g. This there's a big F here is the function that change the f to g. So f must be a continuous map. Here the continuous means we need to avoid the break or jump at the function. If there's a f homotopy from f to g, we say that f and g are homotopic. And if a function is homotopic to a constant map, then we say that the function is a new homotopic. Okay, now we see an example. Okay, let f and g be R to R continuous function, then f is homotopic to g. Okay, we can choose the homotopy to this as like this. So the idea here is that from f to g, I just go straight away with the line segment for each point. So, and clearly we can see that, but here the t means we said that f I is the 0, 1 is the, we can think it as a time. So when t is equal to 0, here is this is 0, we can get fx, and when the time goes to 1, we can get the gx here. So, and here is the continuous function, since the linear combination of the continuous function is also continuous. So clearly this is a homotopy. Okay, corollary, any continuous map fr to r is no homotopy. Okay, we can just use the homotopy here as this f big F here. So is if we think it as geometrically, then this is obvious. Okay, now X, Y, B topological space, a homotopy is an equivalence. So here the equivalence, we have three conditions. Okay, first one is reflexive, then symmetry and transitive. Okay, now we define the homotopy class. Okay, if a space, then there's two functions there, f and g. If f and f is homotopic to g, we can collect them into a class. We denote by this bracket. And if a space there can be a lot of function there, and if, for example, f and h is not homotopic, then they are from different class. Okay, now we see a proposition here. F and Y be topological space, and f prime and g prime be continuous map. And here is basically the composition of the function. If f and f prime are homotopic and g prime are homotopic, then the g composite f is homotopic to g prime or composite f prime. Okay, now, okay, if f is the continuous map and we say that f is homotopy equivalent, if there exists a inverse homotopy, it means that if I take the composite of them, I will get a identity map. Okay, if there is a homotopy equivalence from two space, then we say that this two space is homotopy equivalent, and we denote by this. Now, okay, now I will talk about the fundamental group. Okay, here we let X be a topological space, and let a point be X1, X0 here, and we have a loop inside the space, and the X0 is the base point. Now we collect all the loop. If for example, f and g is a loop there. If f and g are homotopic, then we as I said just now, is from same class, and we can collect all the class from the loop, from the space there, and we collect them as a set. If we can give a group operation there, and we get the group is this one is a group. The group of operation I will give it later, and this group we call the fundamental group of X at the base point X0. This is the group operation. And this, okay, here we take two elements, and F is a loop here, and G also a loop. So we composite them by, we run around go through around F first, then we go through the G. Means we double up the speed. So here is a group, a loop. So we also get a loop. So this is also, this shows that this is closed under group operation. Okay, now a definition, we define H is a path. If you put a bar up on the H, means the inverse. And this I is from 0 to 1. This, if we change the T to 1 minus T, is from 1 to 0. So it's just change the direction. Okay, now this is the change of base point. Okay, we can see that F is a loop at x1 here. So it's a loop. So H is a function from x0 to x1. So we run this, we get first we get H, this, then F, then we go H inverse, we will go like this. So we can say that, you can see that this is also a loop, but the base point is in x0 here. Now, okay, define a beta H is a function from a fundamental group to another group is, okay, now F is a loop in from the x1. Now we change by this as just now as like this. So we can see that this is the change of base point. But this is base point is also in the same space but different point. Okay. Now this the map beta H is isomorphism, means that we change the base point to another point, but we doesn't change the structure of the fundamental group of the pi1x here. Now, okay, let X be a convex subset of Rn. The fundamental group of X is trivial. Okay, I recall the definition of convex set is if I choose any 2 points from the set, then the line segment between that 2 points is also lies on the set. So, okay, for example, this is the space. Okay, I maybe best point here. Okay, I draw a path maybe. Okay, now if I take 1 point here, maybe here. Okay, the line segment between this point and x0 is also lies inside this space. So we can use the homotopy to move this, go this direction, go to near the x0, and we can apply this to all the point. Then we will get a loop like this. This is x0. So we can maybe this is become smaller. Then we will get a go to identity map. So any path from this space can go to the identity map. This shows that the pi1 of this space X is only one homotopy class is identity. So you can see that this is a group with only one element. So this is trivial group. Okay, now we talk about the fundamental group of circle. The fundamental group, this here S1 is the notation for a two-dimensional circle. This fundamental group of circle is an infinite cyclic group generated by the homotopy class of the loop. This omega s is equal to cosine 2 pi s and sine 2 pi s. Here the cosine and sine are periodic function with 2 pi. So we can see that if I take omega s plus k is equal to omega s if the k is integer. So here base point, we did not mention the base point here because we can, as I said just now, the change of base point is isomorphism. So I can take the base point at any point from the circles. The fundamental group still have same structure. So okay, now if I take maybe the one loop here and a two loop here, if I do the group operation, I will go more faster, but the result will be a 3 loop like this. Okay, so I see some path lifting lemma. Okay, now let F be a continuous map and X inside R, and X is inside R, and PX map X to F0 here. F0 here is a point. F maps interval to S1. So okay, if as I said just now, as this omega s is a periodic function. So if P is a periodic function, then there can be many points from the R maps to the same point F0 in here. Now what if I fix a F title 0 to equal to X? then the path from in R will be the unique. So this is the idea for the path lifting lemma. Now you see the homotopy lifting lemma. Okay. Now here I consider there's two path in this S1. Let's call it alpha and beta. Okay, if alpha and beta can be different path, and if I take the homotopy from alpha to beta, and I leave the homotopy, the process of the homotopy will also unique inside R. Okay, we can just use this path lifting lemma if the process of the homotopy is also a path here. So if I leave the process to R for all t, and I will get the process in R is also unique just by using this path lifting lemma for all t inside this. Okay, now we talked about the Van-Kampen theorem. Van-Kampen theorem is let X be a path connected topological space, and let UV be the open subset of X such that U union V equal to the X and U intersect V is not empty and path connected. Then the fundamental group of X is pi 1 U amalgamated free product with pi 1 V under this pi 1 U intersect V. Okay, now we see example. Here the fundamental group of a sphere. And now, okay, we see that this U is this red color part, and V is this blue color part, and the U intersect V is the cylinder here. Okay, now we can see that U is a draw a circle like this with like this. So this is we can press the from a bottom part for the top part. Press down, we can see that this is actually we can see it's a disc. Okay, this is also a convex set, so we can see that the fundamental group of U is trivial. And similar for V, we also can do the same process. Or V also is same with this, so this is also the phi 1V. Okay, now we consider the U intersect V. U intersect V is a cylinder, and if we ignore the height of the cylinder, we can see that this actually is a this is a cylinder like this. We press down, then we will get the circle. Circle is S1. As just now I already explained that the pi 1 F is equal to is isomorphic to Z. Okay. Okay, and Z is generated by 1. Okay, now we see the fundamental group. Okay, now here's the pi 1 U intersect B maps to F with a map from to pi 1 U and another map to pi 1 B. This is G. Okay, this is Z. Z is generated by 1, and this is the trivial group. This also trivial group. Okay, now we have F maps element from this. Maybe we call it C from it to here. Here is only one element, so this is E, and also G element is also E. The amalgamated free product, we need that this is same. As obviously this is very obvious. So this the fundamental group of the sphere is only this color. Pi 1 S2 is the generator in Z is 1, and the relation is E equals to E is there's no any restriction, so it's only the here the generator is E. So is trivial. So here is the notation by the group presentation. Okay. No, okay, thank you. That's all my presentation.
Okay, thank you for your presentation. And Julep, comment, question?
No, I mean, thanks for the presentation. It's very clear. So yeah, so what is your plan? I mean, for the the next part, like, because I'm just curious actually, like, I mean, looks like
next part will
quite a lot in there.
next part will be the covering space, and we'll see the universal covering.
Okay. So, by the way, like, for curiosity, so did you try to find the fundamental group of like, so sphere? So the next one, I mean, obviously like the donut. So
the torus.
Yeah, torus. Yeah.
Yeah. I already find the torus, but I will put the example of torus
This
in
is in the
the
report.
final presentation.
All
Yes.
right. Okay.
And is already written in the report. For the torus, for the Klein bottle, there is another example I think you did. I don't which one. Anyway, thank you, Julie. All this are in the report, and maybe he choose. I told him to choose one example, so he chose the simplest one, and the other example he will present it maybe.
Yeah. I mean,
maybe in the final.
Midterm, like, I mean, we don't have like long time.
Yeah.
Okay. Yeah. So thanks for the presentation. So. Yeah, I mean, not any questions, just curious.
Okay. Thank you for your comment and your question, Julie, and thank you for your presentation. Thank you so much, as I said. And maybe I can stop recording.
Yeah,
right?
I think so.
Yes, you can stop recording here. Yes.